Thanks a lot, Nicole, for that introduction. Nice to see you all. I think I know most of you. If you don't know me, my name is Guy Williams, and I work here at IMAS. Today is a slightly loose talk. I'm actually giving 6 talks over the next 48 hours, and I might have completely messed up which one today is, so hopefully it's somehow on track. I guess it's, without oversimplifying, it's probably just going to be a lot of toys and videos, but hopefully it spawns a few questions, and hopefully we have a bit of time to learn a bit about what I've been up to. I have to do this more and more. It gets very confusing with the alphabet soup. Today we're going to be looking at AUVs and UAVs. So, and I've put these around the wrong way really, but the one goes under the water and one goes above the water. Unmanned aerial systems is also kind of popular. Depending on which country you're working with, drones is either exactly the right word to use or exactly the wrong word to use. So we tend to sort of go with UAS as the best way to describe our platforms that go into the air. I guess the general background, I haven't really spent too many slides on this, but it's all about the so-called paradox of Antarctic sea ice, this idea that somewhat strangely in a warming world, the mean sea ice extent around Antarctica has been relatively robust. That's, of course, if you don't look at 2017, or 2016 rather. But nonetheless, the story is one of sort of somewhat puzzling robustness with respect to what we see in the Arctic, where there's been a very strong decline, something that we would naturally tend to associate with a warming world. I think we've all seen these sort of slides many times before, but the next part of the story is always to say, well, when you look at the mean extent around Antarctica, that's not really a very good parameter to look at. You need to look at the regional changes, and when you do look at the regional changes around Antarctica, you see there are dramatic changes occurring. Quite well documented is the very strong decline occurring in the Bellingshausen. So this isn't necessarily the extent, this is actually the number of ice-covered days per year, but it tells the same story. And in fact, when you look at that retreat in the Bellingshausen Sea area, it's actually on par, or if not stronger than the Arctic declines. What we're seeing is it's getting balanced by an expanding sea ice edge in other areas, most notably in the Ross Sea down here. Now, there's a whole story associated with that. We won't go into that today. That's sort of more in the realms of what someone like Phil Reed might talk to you about for hours and hours on end. What I'm going to talk about is this idea that when we use the satellites to look at the extent of sea ice, it works very well, but we're not getting the total thickness and we're not getting the total volume. So that's a real key missing piece of evidence that we would like to have when it comes to trying to unpack what's happening with Antarctic sea ice. I'm not a remote sensing scientist, but I can understand that in theory, it's relatively easy to get sea ice thickness from space. You can use some basic buoyancy equations to look at the displaced volume of water, and from that make some assumptions about, if you have some assumptions about the density of both the snow layer on top and the ice itself, you can then come up with the total sea ice thickness. It gets complicated when you try and get the key parameters that you need for this. This is the snow freeboard, or the height of the snow above the water, and the ice freeboard. Still, to a simple mind, it's pretty straightforward if you have the right tools, in the sense that a laser altimeter should be able to give you the height of the snow freeboard above the ice. And with a snow radar or radar altimeter that can penetrate through the snow to the snow-ice interface, you should be able to then get the ice freeboard as the difference between the two. Of course, what they don't tell you when you sign up to do this for the rest of your life is that they don't actually put the same sensors on the same satellites, and they don't put the satellites up at the same time either. So it becomes very difficult and quite challenging in that sense. What makes this particular calculation difficult is the amount of snow in the Antarctic. So it's quite sensitive to that snow layer. So they've had a bit more luck with this in the Arctic, where the snow layer thickness is generally much smaller. Nonetheless, the satellites keep going up, and as a result of that, we need to go out and do calibration and validation. And I guess that's where my work really comes in as an observing scientist in the sea ice group. This picture on the left of this artist schematic of the Cryosat-2 satellite just gives you that idea that satellites aren't perfect in the sense that they're not going to give you an instantaneous record every second, every metre of the Earth. They tend to operate on a swath where they take a large average. They also operate in this splodge mode where they're not actually getting data all along. So this is sort of something we need to think about when we're trying to think about comparing apples with apples and doing our calibration and validation. And that swath distance for cryosat-2 is about 15 kilometres. So if they give you a thickness of sea ice, it's going to be averaged over 15 kilometres. And what most people know if they've ever been on sea ice, and particularly if they've done the relatively futile thing of walking around trying to drill holes in it, is that the thickness varies from metre to metre. Over on the left, on the right rather, we just have some indication of some of the hard work that's happened over the years to try and validate the satellites, either by manually walking along a 100-metre line, drilling a hole and sticking a tape measure down, or recruiting any number of honours students to go down on the Aurora Australis and stand on the bridge all night and take visual measurements of the thickness as the ship passes through it. And it's something we bang on about all the time. There's a clear bias in these in-situ observations. Number one, because the ship wants to go through thin ice, so we tend to miss out on the very thick ice. And when the sea ice scientists actually go down and do an ice station, we only have about 1 day, maybe a day and a half at most. And to try and, we generally don't necessarily pick our drill line to go through the very thickest ice. So, matter of fact, actually the thickest drilling estimate is about 5.5 metres if you look at the Aspect database, which has a collection of all the in-situ drill holes around Antarctica. So amazingly, we would come back after a huge amount of effort and a huge amount of money with just something like this for each ice station, which is 100 metres of the snow thickness, the ice freeboard, and the ice draft. And that was what we would publish to try and then validate what's going on over here. So it's been an exciting time to sort of come into this field with the advent of the underwater vehicles. There's a few different vehicles around at the moment. Today I'm going to specifically talk about this seabed vehicle, which came from the Woods Hole Oceanographic Institution. Interestingly enough, about 8 years ago, we were on track to get a very large, big Explorer-class AUV, but for a variety of reasons that didn't happen. But we had a voyage that was going down to do some sea ice, so we were lucky enough to be able to follow in the steps of some British researchers that took this vehicle down to the Bellingshausen Sea in 2010. They had great success with this platform. Different AUVs for different jobs. This is not like the torpedo-shaped ones, which have a long-range capability. This is more of a hovering platform, more like a helicopter, actually. It has the ability to stop, move vertically, turn. So it's very much purpose-built for high-resolution, detailed mapping, mostly of the seafloor and of coral benthic habitats. But they've done that for a few years, and the interesting thing about working with robotics engineers is they don't, unlike us, they don't want to do the same thing over and over again. They want to do different things. So this group, when approached by the British Antarctic Survey, agreed to flip their whole system upside down so that they could effectively survey the bottom of the sea ice. It's a fairly simple system with the main sensor being a multi-beam sonar at the surface. And you see the basic plan for a sea ice voyage. This isn't a long-range mission as such. It's more like measuring a couple of football fields next to the ship. The ship can park in itself into the ice. The X's represent various acoustic transponders. The vehicle doesn't necessarily need them, but that's a backup plan for its navigation. It actually navigates by a Doppler velocity log bottom track on the ice. But you can see clearly how getting pings back from 2 different or 3 different transponders, you can co-locate where the vehicle is in time. I guess the point I'd make about this was we had hoped to get a long-range vehicle, but in fact this was better for us because a sea ice voyage is typically a lot of different scientists doing a lot of different projects on the ice station itself. So to actually have a long-range vehicle go away and sample away from the ice station would have a disconnect. The nice thing about this survey is we're actually measuring the actual flow that all the different scientists are working on, from the physics, the chemistry and the biology. And it was very successful. We came back, instead of having this 1D or 2D line, if you like, the 100-metre line, we had what we now call this layer cake, which I've shown before many times, where we have 3 different surfaces. The snow surface, which actually came from a terrestrial LiDAR, much like you'd see a surveyor using around on the streets. The ice draft below from the AUV, you can see in this particular case it's going down to 10 metres. So again, something that clearly humans would never drill through. And in the middle, the ice surface interface, if you like, or the ice freeboard. And so over the years now, so IceBell in 2010, Cypex2 in 2012, and then just last year in the Ross Sea, this vehicle has been able to move around and collect a lot of new information. It's not, the 3D nature of this is just gives us a new richness of data which we hadn't really seen before. You do get a sense though, this is the AUV track in red, and this is our terrestrial LiDAR survey. So this layer cake, if you like, is only 100 metres by 100 metres. So we still have a limitation in the sense that we haven't got to the scales where we can still make a very nice comparison with satellites. So the great hope was to take a new technology and try and improve the laser scanner surface and to expand it out to try and reach the scales of the AUV, which is now at about 500 metres by 500 metres. And that's where we move into the UAVs. So it was good timing. SciPex 12 being in about 2000, SciPex 2 being in 2012. And it was about in the early 2014 that this sort of new age of very easy to fly, very cheap and affordable drones started to emerge. It's quite an interesting field. I've talked about this before. The rapid change in this technology is incredible. Every 6 months something comes out that's better and often cheaper than what you had before. So you're in the unique position where it's actually to your advantage to crash the drones, often. This one's a good example. You might have seen it sitting outside, out of the mechanics lab window. It's basically a museum piece now. It was the state-of-the-art $10,000 drone capable of carrying a large Panasonic digital SLR camera. And within 6 months, one of the small quadcopters came out with an inbuilt camera that had the same capabilities. So it was now only $2,000. Nonetheless, it was very useful to get out there and start to use it. The very primary use for this one initially for a sea ice scientist was just to try and grab very quickly a picture of the sea ice, the flow size distribution, if you like. Sort of this sort of image, which was, you can essentially get in about 10 minutes when the ship stops as you move through the sea ice zone. There's different uses for the different types of drones, especially the multicopters versus the fixed wings. The multicopters are very useful in terms of taking off and landing in a very small space, like on the back of an icebreaker. It's quite challenging to do that with a fixed wing, but ultimately a fixed wing is always going to be more aerodynamically efficient, and so you're going to get a much greater range and coverage. And so we started to develop a new platform for doing this, together with the... we're very fortunate here at UTAS. If you're not aware, we have a very world-leading UAV facility at Terra Luma, based with the Spatial Department of Surveying. And they're very open to discussing different ways of applying this technology. And they were very, very helpful in setting up this fixed-wing system, which we can see just being deployed here in the Arctic. So it's about $100 for the airframe, $500 for the brain inside, and then you drop a Sony Alpha camera, which is about another $1,000 on top of that. So about $2,000, you're off and away. And it's flying autonomously. So again, like the AUV, you can send it out to do its own little missions. I don't know if you can see that very clearly. This is probably about a 10 to 15 minute mission conducted at the early stage. And with a very good camera, you can get this incredibly high resolution imagery. And around about the same time as these advances in the hardware, we saw great advances in the software available for photogrammetry. That's the ability to take these 3D images, even if they aren't geolocated with no GPS reference. You can set up it using structure by motion if you have enough overlap to get not only an orthomosaic like that, but actually a full 3D, oops, oh, it's that video, full 3D digital elevation model of the snow surface. This is just showing that it's, yeah, once you have a few of those crashes in the snow, it gets a little bit nervous when you throw it off a ship. It's a good moment, until you realise you've got to land it back on the ship, and that you left your cargo net back in Australia. So we had to use this one on the... I'll probably stop it now. Yay. Sorry for everyone that's seen that 100 times. Yeah, this is the software I'm talking about, where it's quite, yeah, it's amazing if you haven't seen it in operation. It's becoming more standard in a wide variety of applications, but the software can very quickly, just from stitching together the photos by itself, again with no geolocation, can work out the orientation of all the camera angles when each photo is taken, and then build a dense point cloud from which it can make this digital elevation model, which we hope to see if we could actually improve upon the LiDAR. Maybe not in the accuracy itself, but on the overall spatial scale that you have to compare with the AUV. And so this was the result, I guess. Again, we have the AUV survey, but now we have a much larger surface survey from the UAS. We went down last year and did this in, I guess, the middle of autumn. So this is actually, I think it's about 11 a.m. And you can see the huge long shadow from the ship, so not a lot of daylight available. We were able to boost the range with a better battery payload, and we were getting about a kilometre by kilometre grid, and we're able to get out the 3D model this way. This time, previously, we weren't really able to, actually we didn't even know they were going to fly, to be honest, so we actually didn't do our ground control very well, and so we ended up having to use the LiDAR data to reference our own digital elevation model. But this time around, when we went to the Antarctic, we were able to do them independently. So it was a nice way to actually compare what the LiDAR was getting compared to the digital elevation model from the UAS. And I haven't labelled these, which is annoying. The one on the left, the black one, is actually the terrestrial LiDAR. And the one on the right is from the UAS. So the LiDAR actually was coming back at about a 10 centimetre pixel resolution for the data, which we were quite surprised. We expected to get much better from that, but apparently that was all they could really do with the wobbling of their, in the wind of their units. The drone came back with a 3 centimetre pixel resolution, so we actually had to subsample the LiDAR to do a comparison. You also notice, quite interestingly, that the LiDAR has a lot more gaps in it. That's because at a lower level, the terrestrial LiDAR is having shadowing occurring, and you actually end up getting a lot more data. And I should just point out, the LiDAR is a $250,000 unit, so it's really interesting that we can get this with $2,000 over a much greater scale from this small drone. We're finishing up pretty soon, so hoping to use these technologies in a bit more in the future. In particular, one area we've been trying to target is the marginal ice zone. It's an area which we tend to just zip through after we've done our ice station studies. But we think now with the drones and the AUV below that we can get the sort of range we want, up to 10 to 20 kilometres, to try and measure that well. In terms of the AUVs, we have a discovery project to buy the next generation seabed vehicle from Woods Hole, which is going to be capable of 10 to 20 Ks. And maybe in the future, after they've stopped going under ice shelves and hopefully coming back from them, we might have a chance to use this under some sea ice too. Now, I think that might be just about it. I'll just finish this by saying we're also working on long-range drones. We've now just done a 10-kilometre out and back with our fixed wing. And this is one of the new Phantoms flying 3 kilometres off the coast from Japan to find the marginal ice zone and take multispectral and visual imagery at the same time. And I'll finish there. Thank you.
Oh, that's the last slide. Okay, I'll let Jackie take it away. Cool. So I'm Jackie. I'm a geologist here at IMAS, working with the Antarctic Gateway Partnership. And today I'm going to just give you a little snapshot of a project. It's actually an Australian Antarctic project that I'm leading, and it also links into the work I'm doing with the Gateway Partnership as well. I know that geologists are a bit of an endangered species at IMAS, so I'm going to keep this pretty broad introduction. I've tried to make it fairly introductory. And hopefully you'll come away, if you don't already know something about Gondwana or what an origin is, you might know what those things are by the end of the talk. That's one of the aims. So this is not about the Southern Ocean. I got squeezed in between two Southern Ocean people, but basically I am looking for an ancient ocean, much older than the Southern Ocean. So we know that Antarctica was a keystone in Gondwana, and here's Antarctica in the present day. or the present day, as a geologist likes to say, 0 MA, or 0 million years ago. And I'm going to show you a little movie, but it didn't quite work there, so I'm just going to bring it up independently. And this is movies thanks to Joe. Hopefully it works. Okay, start it again. So basically we're going back through time. I'll just try and start it again. From the present day back through geological time and the millions of years up in the corner there. And you can see the continents moving towards Antarctica to form Gondwana. So you can see the Southern Ocean is disappearing. That's the last we're going to see of it in this talk. And India comes in, Africa comes in, South America. And so by 200 million years, at least these parts of Gondwana are together. And this reconstruction is fairly well accepted. Well, at least the main parts of this reconstruction are fairly well accepted. And that's because we've got ocean floor, which we can use. The ocean floor has a magnetic signature, or seafloor stripes, as you might know them called, and we can use those stripes to infer the age, and then we can basically remove seafloor of different ages as we step back in time. So ocean crust is really handy for reconstructing continents, but what about if we want to go older than 200 million years? And that's what I'm interested in doing. So what about older than that? How did Gondwana assemble? So Gondwana assembled between about 700 and 500 million years ago. These are big numbers, and sometimes it makes your brain explode. But that's kind of the time period that we're looking at here. So how do we go about finding these ancient oceans and ancient continental boundaries? Well, if we think about the theory of plate tectonics and what we know that's happening on the modern Earth, some images here, when two plates come towards each other, the oceanic crust is more dense and thinner, and it gradually subducts beneath the continental crust, which is more buoyant. And so as these continents collide, we get a volcanic arc, usually, a chain of volcanoes that is produced in the overriding plate. And as the ocean floor continues to subduct and eventually falls off and falls to the deeper parts of the Earth, we can get a little bit of remnant ocean crust called a suture zone that's former parts of the ocean floor, deep sea sediments and so on that are squished in there. And we also get a mountain belt or an origin or an orogenic belt. That's where the word origin comes from. So we're looking for suture zones, we're looking for volcanic arcs, and we're looking for metamorphic rocks and plutonic rocks that form in these collisional belts. And so each stage of this continental collision process produces rocks with different properties and with different geochemistry, and we look for that in the rock record to give us some clues as to how the continents moved in the past. So how did Gondwana assemble? Well, the paleomag data tells us that India and part of Antarctica that was attached to India, of which we don't know how much yet because we haven't done enough research, was north of where Australia was sitting at 700 million years, by about 30 degrees north. So the idea is that there was an ocean called the Mawson Ocean that separated Indo-Antarctica and Australia-Antarctica before Gondwana formed. And by 540 million years, these continents came together along with other continents here to form the Gondwana supercontinent. So the Mawson Ocean, it lived and died by 540 million years. And the collision of this India into Australia and Antarctica formed what we call the Kunga origin through here. It's really not well understood, and that's mostly because it's not well exposed. So you can see that it skims the Western Australian margin and basically doesn't exist onshore. In India, it's sitting here, but it's mainly been subducted under Asia, or it's covered in sedimentary basins. And then in Antarctica, it's basically hidden under the ice. So it's not well understood. It's thought to be the last suture that stitched the Gondwanan continent together, but also that's quite controversial. And there's no volcanic arc or suture zone rocks exposed that we might expect, as I showed in the last slide. We haven't found those yet, so it's not sort of like a typical orogenic belt. And that may be just because we haven't found those rocks yet because of the exposure. So how do we go about looking at that problem in Antarctica? Well, it's a pretty unique challenge to do geology in Antarctica, basically because we've got less than 1% exposure, so we have a very thick ice cover, and also because it's very expensive to get there and to do field work logistically, sampling the geological outcrops is quite challenging and dangerous, so it doesn't happen all that often. So we use the geology and we combine it with the geophysics so that we can look beneath that ice sheet to understand the formation of the continent itself. So what was our approach? Our approach was to combine new geological observations from new samples that have been collected and also from archive samples that exist in various collections, to do some age dating to find out how old those rocks are, and then to combine those geological observations with the geophysics to tell us something about the underlying crustal structure. So these results feed into, global models of how supercontinents have evolved through time, but they also have implications for the geological architecture of Antarctica, how that affects the geothermal heat flow, how we can reconstruct ocean currents and glacial dynamics in the past. But I'm only going to talk about that first topic today. So the geophysics, that basically gives us a roadmap of where to focus our geological observations, which is on a much smaller scale. So there's been some great geophysical campaigns in the last few years. This image on the left is a gravity image from the IceCap program, which Australia is very involved with and is ongoing. And you can see here that in this context, the geophysics in Antarctica has been interpreted in light of what we know about Australia, where the geology is much better known. So we can take the structures and the provinces that we see in Australia and project them into Antarctica. And that's been done, and there's been various interpretations of these data. And what I just want to point your attention to here is this lineament here outlined in red that's been interpreted as a suture zone between Indo-Antarctica, all these terrains in brown, and Australia-Antarctica, the terrains in blue and green. So this was kind of our roadmap that we're going into this project with. This is the most recent interpretation. And can we get on the ground now and test that interpretation? Is this the missing suture zone that is our plate boundary that we're looking for? So what do we do first? First, we want to fingerprint the age signature that we're looking for the crust on either side. What's the Indian fingerprint? What's the Australian fingerprint? And then how can we use those unique fingerprints to look at the boundary between those crustal blocks? So first we look to the marine record. And there's a wealth of cores, the little dots here, and not many over this side, but you can see 3 here. They're placed in a Gondwana reconstruction here. So this is the cores sitting offshore Antarctica, but we've put them in a plate reconstruction here that shows our area of interest in here. Here's this previously interpreted suture zone structure running through here. If we compile all the age data that's available, and in this case this is from tiny little zircon grains, which are sort of 100, 200 micron long, here's what the age spectra looks like. So 0 million years present day back to 3.5 billion years back here. And in pink, we've got all the Indo-Antarctic data. You can see a high peak around 940 million years and also a younger one. And in orange, the Australo-Antarctic data, which has a common peak at 1190 to 1140. So we take these 2 age signatures as diagnostic of India and Australia, respectively, along the Antarctic coast. And we use them to find a boundary between those blocks. If we look at what's known on the onshore geology, just from those tiny little outcrops that we know about, it follows a pattern that shows that probably crust of Indian affinity extends as far east as Mooney Station, but there's really not that much known from that region at all. So let's zoom into that critical area. So this is a LEMA satellite image just to show that area of interest that we're looking at. And just to highlight that there's really hardly any geological outcrop at all. So that's what we're dealing with, and that's why those few locations that are highlighted were really important to try and get some samples from. So if we start in the east, we know that the Bunga Hills, which is quite a substantial region of rock outcrop, we've known that that has an affinity to Australia, and we've known that for some time. Some more recent work has done some really detailed dating in there, and we now know that it's part of the Yilgarn Craton of Western Australia. So that's fairly well established. Here's the lineament that we're testing as the suture zone. So let's step west now and look at some of the new age dates that we've obtained. So here's a little zircon. These are the little guys that I'm shooting with a laser to understand the age of these rocks. So here's 100 microns, so they're pretty small. And they're very intricately zoned usually, like a bit like tree rings. We can date different parts of the zircon, so we can typically get several ages out of one zircon if the rock has undergone a complex history. So in this case, you can see the centre is 1600 million years, sorry, and the rim here is 1200 million years old. So 400 million year difference in core and rim in this particular case. So the important thing I just want to point out here is, and that's why these parts are circled, I won't go through how you read these graphs or anything, but the gneiss that we got from the Bruchev Hills has a metamorphic age of 1140. The gneiss we got from Cape Harrison has an intrusion age of 1190. And they both overlap with the Bunga Hills, and this age signature that we've defined is typical of Australian rocks. So we interpret that part as Australian. So notice we've already crossed over the previously interpreted boundary zone now. So let's go west again, and we've got some new samples from here. But all the samples, all the rocks we've got in here are plutonic rocks, so like the east coast of Tasmania, granites, diorites, gabbros. And they all come in around 530 to 500 million years, so a lot younger. But they're intruding into basement rocks that are very, very old. So this is 3 to 2.6 billion years old. It's a very ancient crust. So that causes us a little bit of a headache, because that doesn't fit with our signature of India or Australia that we'd previously defined from the offshore record and what we know about previously onshore. So could this little wedge in here be a completely different continent altogether in the past? That's possible. We actually think that it's part of Australia, and I'll just quickly go through why, but it actually relates to what we know about offshore. So here in this crucial part of our reconstruction are some tiny little microcontinents that fit right in the wedge between India, Australia and Antarctica. And we have gone out and sampled these microcontinents in the last few years and have proven that they are in fact continents, they're not oceanic rocks. And they started their life sitting here in Gondwana, but as Gondwana broke apart, the naturalist plateau here was stretched as India started to move apart. It still sits offshore Australia now. But the other two little continents, Batavia and Golden Knoll, they went with the Indian plate until a certain time, about 100 million years ago, India changed direction and went quickly north towards Asia. And that tectonic forcing actually broke off those little continents, and they sit beneath kilometres of ocean in the Indian Ocean today. So if we reconstruct these little guys back here, they're really crucial to our story. So this is where we were before in Antarctica, and we can see that the ages we get from the dredge samples do have an Australian signature, and they sit in this key area. So by implication, I guess, we're suggesting this area is also Australian. So that brings us further west again. We know that we're in India over here, so we're looking in this region for a plate boundary. And we look to the geophysics, we find that there's been a fault identified, and we suggest that this might be the plate boundary. That might be some strike-slip movement on this plate boundary, similar to what we see in New Zealand along the Alpine Fault, for example, the boundary between two plates that's just sliding past each other rather than colliding head-on. And how might that move inland? So that's kind of fun to think about and important to think about if we want to try and move this research into a sort of a global perspective. So here we are with our observations on the coast. We suggest this Murni Fault might be the plate boundary between India and Australia. And if we go inland, we can look to what the geophysicists can tell us about the interior. And there's been a lineament in there thought to be a suture much older age, but we're suggesting perhaps these are linked. And the Gamburtsev Mountains, which are the tallest mountain ranges in Antarctica, sit right here. And so potentially they are related to this feature. So we would interpret strike-slip movement here, so sort of like alpine fault type movement along this section of the plate boundary. And then as we turn the corner, we predict head-on continent-continent collision, leading to sort of Himalayan-style mountain range building in this area, producing the Gamburtsev Mountains. So we would predict that all that arc magmatism, the suture zone rocks that we haven't found yet, they should be in this part of the plate boundary. So that's convenient for our story because they're hidden, right? So that's, you know, this is quite speculative, but there is plans to drill the Gambetta Mountains in coming years, and the Chinese and the Americans are really looking to do that. So it'll be interesting if we can get a better idea of what's underneath that ice. So I'll just quickly say how that links to my gateway work. We know that these granites that I talked about, these 500 million year old granites, are really radiogenic. So they've got a lot of uranium and thorium in them. So they're really hot, and they're pumping a lot of hot heat to the surface of Antarctica. And that's important because the ice sits directly on those rocks, and it controls the temperature field at the base of the ice, particularly in the slow-flowing areas. So it's been shown that these granites, we know that they're just west of the Bunga Hills. They're also all along the Prince Bay coast, which is through here, and we also find them in the interior of Prince Charles Mountains along the Amory Ice Shelf. They are particularly hot relative to normal average granites, and we think that they are quite important in producing hot spots under the ice sheet. So understanding where they are and mapping them is important, and something that I'm also working on. So I'll leave it there. Thank you.
Okay, sorry. Thanks. Okay, so today I'm just going to give a brief overview of an international initiative called the Southern Ocean Observing System, which is hosted here at the University of Tasmania. I'm going to take it for granted that you all understand the importance of the Southern Ocean in the climate system and why we need to observe the Southern Ocean. I'm sure many of you are aware of the global effort to observe the world's oceans. This effort is done primarily through a network of regional observing systems, such as the Australian Integrated Marine Observing System, or IMAS, which is also hosted here at the university. These regional observing systems are overseen or governed by the Global Ocean Observing System Program, or GOOS, and that really facilitates connections between these regional networks. SOOS sits down here, the Southern Ocean Observing System. Our governance is not, or we're not officially part of the Global Ocean Observing System for a number of reasons. Our governance is different, and I'll go into that in a minute. But we do have overlap with a number of the regional observing systems. As you can see here, our northern boundary sits at about 30 degrees south. So there is overlap with these regional systems, and we do work closely with the GOOS community where there's overlapping interests. So SOOS is an international initiative of the Scientific Committee for Antarctic Research, SCAR, and the Scientific Committee for Oceanic Research, SCORE. So they're our governing bodies rather than GOOS. We're also quite different to these other regional observing systems in that we don't have control over the resources that go to putting observational kit in the water. So we don't fund observations or data management activities as such. Rather, we work by bringing together and integrating all the different efforts, all the different national and international efforts to make observations of the Southern Ocean. And there is really significant investment in observing the Southern Ocean. I just wanted to highlight here a couple of the internationally coordinated programs that observe not only the global ocean but have significant focus on the Southern Ocean. And these internationally coordinated programs have really fundamentally changed not only our understanding of the Southern Ocean, but also our ability to observe the ocean in a sustained way through development of new sensors and technologies. And one of the keys to the success of these programs is that they generally focus on one or two variables and one observing platform, and don't only coordinate the collection of the observations, but importantly also get community consensus on things like standardisation of methods, the sensors to be used, coordination around the spatial and temporal requirements for the observations, and then importantly also do data management and delivery in an open access way, which is really important to the success of these programs. So they're really key and significant contributors to SUS. There are also many nationally funded and multinationally funded observing projects in the Southern Ocean. So SUS is trying to bring and integrate these nationally funded projects with the internationally coordinated programs that I showed earlier. These nationally funded projects, and this is just a few of them, there are many of them, are generally more multidisciplinary. They use a large variety of observing platforms, and the methods used and the data management standards are all decided by the individual chief investigators. There's no sort of impetus to, they don't have to use international standards. So there's a huge variety in the way the observations are made. These are also really important contributions to SUS, and many of them are short-term project-based funding, but there are some others like the US Palmer LTER program, which has been going for over 20 years. So we're looking to really bring together these different observing programs. And that brings us to the mission for SUS, which is to facilitate the collection and delivery of essential observations on variability and change of Southern Ocean systems. And we do this through the design, advocacy and implementation of both a cost-effective observing system and also a data delivery system. So what does that mean in practice, and how do we achieve this? So SUS has developed two key mechanisms to achieve this mission. We have developed a number of implementation groups, which is shown here. We have subcommittees, working groups and sort of short-term focused task teams. And we've also worked with the community to develop a number of data tools and products and coordination tools. So I'm just going to highlight 4 of them here today, which I think will be of most interest to you all. And the first one is that I wanted to highlight is the regional working groups. The SUS regional working groups are really focused on integrating and bringing together all the different observational activities within a region. We have 5 regional working groups that you can see here, and these are based on the natural areas of focus of the different nations. So it's based on the national infrastructure and focus of all the different nations. The objectives of the regional working groups are to look at what the big gaps are in observational coverage within a region and work on advocating and enhancing those observations and filling the gaps. To look at standardisation of methods across different observing different variables. To ensure that any data streams coming out of these regions are both discoverable and accessible. To work towards designing better observing systems within the region, so asking the question about what is the spatial and temporal coverage that is needed, and more generally to coordinate field activities and share resources and align projects. The nations that I've listed here are by no means final. This is just an indication of those nations that have been involved in the regional working group activities so far. They're fully open, and I'm more than happy to chat to anyone who's interested to get involved in these groups. So the second thing I wanted to highlight here is the SUS capability working groups. These working groups are really important in enhancing our ability to observe the Southern Ocean, and they might do that through, for example, development of new technologies or methods, through improving observational design. They might be to drive coordination or building of networks towards enhanced observations, and they may also focus on some element of data discovery and delivery. We have several capability working groups. 4 of these are quite well established, and 2 of them are just in development now. Again, these are open for engagement with anyone who's interested in any of these groups. And I'd encourage you to go to a website, although it is out of date, so you can get some information on some of these working groups, and we're hoping to update it within the next few months to include all of them. Okay, the next thing I wanted to highlight was a new tool that SUS has been working on over the last year or so called SUSMAP. SUSMAP is delivered for SUS by eModeNet, which is a European data network. And this is an online tool that delivers integrated data sets through a web interface. So all data, for example, that you can find in JCOMOPS, which has the Argo floats and the Drifter buoys and others, are sucked up and delivered through SUSMAP. There are other data layers, such as, they haven't really shown up here very well, but there's yellow diamonds here. These are Southern Ocean moorings. SUS has worked to identify nearly 700 moorings that have been deployed in the Southern Ocean over the last sort of 30 years, and these are now also delivered through SUSMAP. You can search based on a platform. You can search based on variables or parameters. There's a time slide at the bottom here. At the moment, I've got it showing all observations or all platforms, but you can make it to the most recent, so you just see what's currently in the water. And if you were to click on one of these points here, you would, or to hover over it, you would get the metadata for that platform. So this one here is a green dot. It's an Argo float. And it gives you a bit of information about what that platform is and the data that you get. If you click on that, it takes you to another screen where you can actually explore the data and download it directly. So that's for all the data that we're getting through JCOMOPS, where the data itself is delivered. There are other layers like the yellow squares, the mooring data. We haven't yet got that connected directly to the data, but that will give you a URL where the data can be found. We're working with the community to add new layers all the time. This is a list of the platforms that we're currently showing through SUSMAP. Just recently we've added the macro and microplastics from the SCAR database. This is the mooring network, as I mentioned, and there are other layers that we're adding. So wherever there is a data community that is pulling together data, doing some QC and delivering it from one location, we can work with you to get that visible through SUSMAP. We also provide a number of base layers. So this layer that you see here underneath is the NSIDC monthly sea ice mean as a base layer, so you can look at what data is available around the sea ice edge, for example. We have other data layers here, or base layers, sorry. For example, you can search what data is available within a CAMLR NPA or other CAMLR areas, or you can lay down the base map of the sea surface temperature product. And like I said, we are working with the community to try and enhance this all the time. So we're definitely open to any feedback or comments you have on this product. And it's available from the SUS website, which you can see here. There's a link to it from the homepage. Okay, the final thing I wanted to highlight is another product that SUS has developed over the last year or so, called Due South. Due South is the database of upcoming expeditions to the Southern Ocean, and this is delivered for SUS by the Australian Antarctic Data Centre. And this is really a tool to support collaboration and field planning. So this database, you can use it to add an expedition, and by expedition I mean it could be a voyage, it could be a flight, it could be a traverse. You can search the existing expeditions. You can create a project, so if you're deploying a mooring on a specific voyage, you can go in and you can add your project there, or you can search for existing projects. So it enables users, for example, if you wanted to deploy an Argo float but you didn't, in a certain region, but you didn't know which vessel was going there, you could go to search expeditions and have a look at the upcoming voyages. So if you were to click on search expeditions, it would take you to this page here where you've got a scroll through table of all the different voyages. In blue here you have the upcoming voyages. Green is whichever one you've selected, and orange is a underway voyage. You can filter the search based on region or different requests here. And if you were to click on the voyage within a table, it will give you information on who's in charge of the voyage and whether there are berths available and what capabilities the vessel has. So it's really meant as a tool to help you plan in advance a way for you to get out in the field if you don't have the logistic support, for example. At the moment, it's based, it's updated predominantly through either you, the users, adding your voyages and projects, or through the SEUS data officer manually searching different nations' logistics websites and updating it. But we're in the process of making automatic feeds from the different national Antarctic programs, logistics databases directly to SEUS, to Due South. So at the moment we have the the JCOMOPS feed going straight in there, so we have all of the Go Ship transects in there. We're working on the Australian one getting updated automatically, and the RV vessels also they're working with us to get them sucked up automatically. So we'll be slowly doing it in a way that this is maintained without the need for individual researchers to go in there and update it. So, as I mentioned, SEUS is really all about trying to get you guys, working with you guys to deliver the tools that you need and the networks that you need to enhance observations in the Southern Ocean. And so I'm more than happy to chat to any of you if you're keen or interested to be involved in anything I've highlighted. That's my email there. And I just want to thank the SEUS sponsors that make it all possible, in particular the core sponsors who support the International Project Office, which is here at IMAS. Thank you.
Pathway to like a long-term monitoring system? Is it really just as calibration against the satellite data, or is there a pathway to turn these to kind of sustain long-term?
Yeah, okay, good question. I hope so. I think the calibration aspect is just one specific physical component of the study, so I'll probably have lost over to the other aspects of both the AUV and the biology that's going on there as well. In terms of long-term monitoring, which is going to come first, I'd say probably the AUV will get there first, but it's still a long way off. One of the things we get told to decide is how you can stop and recharge an AUV. So it's something that everyone thinks may be easy, but that's no kind of money that hasn't really occurred yet. You do hear about it, these sort of meetings where they go, well, what's coming next, what's a good idea. Potentially you could have a system at a base where a long way to go out, come back, recharge, and do that for a good day.
The microcontinents, do you have any parts spread out around Antarctica? Just kind of common concept? No, that's so weird. But yeah, that was great and all that. But thinking a couple more, how is it going to actually put it around like a block? The part, and then actually the lava system that was there, that they can later. So in that sense, there's a much more visible. The Ellen Bank is social media and like that. And that's what the microcontinents that lifted up and broke up. I guess they want that. They have some on the ice cap. So the definition of microcontinents means more blocks. Microcontinents are more but now we start with one continent on the one plate. Yeah. So microcontinents, I guess the definition is it's a continental material surrounded by ocean crust. And so they have to be separated by ocean crust. So we don't see them completely. and wonderful leads. This is great. Do you get much,
Sorry.
as far as the data goes, so all the data that is, for example, on the Antarctic data center is directly into SUS. So if you go on SUS, you find all the last chemistry, biology, everything. It's just all computers data.
So I guess there's sort of two aspects to that. We're fully multidisciplinary, so we're interested in not just physics data, but all the way through to biological data. At the moment, data, for example, in National Antarctic Data Centres can all be accessed if you go to the NASA GCMD, which is the Global Change Master Directory, which is a metadata search tool, if you like, that harvests the metadata from the National Antarctic Data Centres, or gives you access, gives you a view of what is in the National Antarctic Data Centres. The problem for SUS is that a lot of oceanographic data, especially physical oceanographic data, is not necessarily hosted by National Antarctic Data Centres, but more oceanographic data centres. And so for data that's not integrated by a community like Argo and delivered in sort of one package, if you like, we're working with the Arctic community to build a federated search tool that can be, I hate the saying, but like a one-stop shop where you go to a site and you can search National Antarctic data centres and oceanographic or thematic data centres that host Southern Ocean data. And then you will get, echinoderm counts or, whatever. But for integrated data sets, we're trying to push them through SUSMAP. So there's kind of two ways of approaching it, because there will always be data sets that are not integrated by, where there's not a community that's pulling it all together and delivering it. Hi.
And what do you do in terms of looking at it if you get the same data more than once from different accidentally or do you actually have how to check it?
So are you talking about for SUSMAP, the map that I showed there? So we're basically, we harvest the data as it's given to us by the community that's managing it. So you might have noticed there's a couple of drifter buoys in the middle of Antarctica. That's a mistake that comes from the original data. So I guess in terms of duplication, we just make sure we go to the community or the network that is delivering the data in for integrated data sets, it's usually just the one community that's delivering it. For the other data, like what Delphine was asking about, where there might be duplicates of individual data records, that's usually for programs that don't integrate and pull it all together. So a good example, I'm not answering this very well, but a good example is the mooring network. That's one of the problems we're having with having direct links to the moorings through SUSMAP, is that all of the mooring data is located in lots of different locations. And we can find links to that data or to a certain copy of that data, but bringing it all together is a much bigger issue.
And you go as far as back to time as you can in terms of having the data, all the data available.
Yeah, so as far back as the data sets that we're sucking up, we will show them. So that if Argo floats went back 30 years, we would show 30 years of them, for example.
Yeah, that's the maps, a couple of the maps that you showed. So there was one that showed basically lifting or melting ice off the entire continent.
Mm-hmm.
And then the one to do with gateway work where you had a map of the heat of the rocks underneath. So how do you generate those type of maps where you can see through potentially kilometres potentially ice?
Yeah, so I think you're referring to the NASA image that I showed. So that's from the BedMap 2 products. So that's a sort of international effort that has integrated a whole bunch of observing systems to understand the ice surface, but also look beneath the ice at the ice bedrock interface, so to understand the ice thickness and then to get a topography as well. So they're sort of much anticipated data sets, and there's been a BedMap and a BedMap 2 release that I know about that have come out, and those data sets are used by ice sheet modelers, geologists, all sorts of people, so they're really valuable. The geothermal heat flow maps that we're trying to produce, so that's quite challenging because, again, the access to the bedrock is hampered, but we're doing that by combining our geological observations with the actual rocks, where we can measure something, with geophysical proxies as well. So that includes seismic data, which of which continent-wide models exist, that they're very interpolated, so the resolution is very poor. But also magnetic data, and that involves both satellite and flight-based magnetic data as well. So the resolution on magnetic data is better in most cases, but it's still, we have to then turn magnetic data or seismic data into temperature. So that's taking an Earth's property and then converting it using a lot of assumptions about how the structure of the crust and of the sphere is in particular regions, making some very broad brush approximations and converting it to a temperature field. So it's quite challenging, and that's, I guess, why the field has not progressed very far in actually integrating real geological data into it, which is what I'm trying to do at the moment, but yeah, it's challenging. I guess the ice sheet modelers, it sort of depends on the resolution you need for the question you're trying to ask. So the ice sheet modelers need some estimate of geothermal heat to put in their model to get it started. It's one of their boundary conditions. And at the moment, they might use a standard or a constant across the whole continent, which we know is implausible. So, you know, every iteration of this process is more accurate and hopefully helps to narrow the uncertainties in the eventual output of a model, ice sheet model. Yeah. 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 So the compilation I showed of the offshore record, that was just data from the literature. So we used whatever was available. We didn't go back and look at the individual images that the authors had provided. We just took at face value the data sets that were provided and integrated them. In my own work, when I've done the dating on those sites that we stepped through along the coast there, I'm imaging every zircon that I'm analysing and making sure that I'm only analysing zircons where I can actually see the full resolution and make sure that I'm not mixing a laser spot across two zones, for example, which would give me an age that is geologically meaningless. So, yeah, so in that sense, it biases the record to the larger grains.